Okay, so the topic today is invariants, graph invariants. Invariants can be met and found throughout mathematics. Everybody talks about invariants. I'll tell you what they are in just a moment. They're a way of capturing graph properties. Graph invariants are. So what are properties? There's a formal answer and there's a less formal answer. The less formal answer is a graph property is something like a collection of graphs, a class of graphs or whatever, that is closed under isomorphism. So the property of having 7 vertices, exactly, the class of all graphs that have 7 vertices form a property because isomorphic graphs have the same number of vertices, right? Graph properties can be captured somehow by particularly simple graph properties, which are determined by graph invariants. What's an invariant? You can think of it as a function that assigns to every graph something. Now, if there are any logicians amongst you, then you will be shuddering with horror when I speak of a function that assigns to every graph something. If you're not a logician, then you can smile and relax. The main thing is that whatever this invariant assigns to a graph is the same something when these graphs are isomorphic. So a function that assigns things to graphs and the same things to isomorphic graphs. These things can be numbers. Often they are numbers. Often they're integers, natural numbers. They can be something else. They can be a group. Anything. Any mathematical object that can be assigned or can be assigned to a graph. And the main point is that isomorphic graphs get the same things assigned to them. So when you think of the class of all graphs as living in this space here, then we may want to describe the graphs that have a certain property. Maybe this subclass of all graphs. And the way to capture it, to describe it, may be in terms of graph invariants, that is, particularly simple properties. For example, we can divide the class of all graphs into those that have minimum degree, I don't know, bigger than 3, and minimum degree at most 3. Right? And in similar ways, we can divide the class of all graphs using some other particularly simple graph properties given by certain invariants like delta or alpha that assign the same value to isomorphic graphs. Or, for example, here, I don't know, we might be assigning a group, and these graphs might have an abelian group, and these might have a non-abelian group assigned to them, or whatever. All right? Okay. One particular application of invariants, now graph invariants, is to certify that two graphs are not isomorphic. Now, when two graphs are isomorphic, and I want to persuade you that they are, then I have an easy task. I'll show you the map, the bijection between the two vertex sets, and then I walk through the edges and the non-edges in one, and I'll show you that the images are adjacent or non-adjacent accordingly. Right? And if I manage to do that, I'll have persuaded you that this map is indeed an isomorphism, and in particular that the graphs are isomorphic. But how do I persuade you that two graphs are not isomorphic? Not so easy. Right? We could, in principle, go through all the possible maps and then check whether they're projections and so on, and if they are, whether they preserve adjacency and non-adjacency, and then determine in this way whether one of them is an isomorphism. But that's a tedious thing to do. And with finite graphs, it is possible to do that, but tedious. And with other objects in mathematics, it's not algorithmically possible. So, for example, when you want to decide whether two knots are the same, the definition of when two knots are isomorphic is a complicated definition, but it involves one way of, the natural way of proving it involves, well, there are two natural ways of doing it. One involves homomorphisms between free space with a knot cut out. Another involves how to relate two particular maps of S1 to free space to each other, so that you can transform one image into the other image without crossing itself. That's another way of formalizing it. Both these ways of formalizing the equivalence of knots are very, very non-computable. So one looks for easy, simple, easy to compute invariants of knots, and we look for particularly simple invariants of graphs in order to give ourselves some tools to persuade other people that two graphs are not isomorphic. So, for example, number of vertices is an invariant. And if I show you that one graph has 5 vertices and the other graph has 6 vertices, then you will believe that these graphs are not isomorphic, and I have an easy job. Similarly, if both graphs have the same number of vertices, but one has a vertex of degree 2 and the other doesn't, that's also easy to check, then the graphs cannot be isomorphic. Right? So that's what invariants are for. And in graph theory, much of our work consists of relating invariants to each other. Right? One invariant might imply another, or certain values for one invariant might imply certain values of another invariant, and that's what we'll be studying in this course. Okay, so let's list a few invariants. Here's one that we had already. Well, not quite. G is a graph, and delta of G is the minimum degree of that graph. That is the degree of a vertex that is as low as possible. So if this is our graph, right, and this has minimum degree 2, because this vertex has degree 2, and no other vertex has smaller degree. And similarly, big delta of G is the maximum degree. So this graph has maximum degree 3 because there exists a vertex of degree 3, but there is no vertex of higher degree than 3. Okay? And then there's a slightly more interesting invariant, that's the average degree. Right? What's the average degree? Well, what the name says, you sum over all the degrees, and then you divide by the number of vertices. So that's the sum over all vertices of G of the degree of those vertices divided by the total number of vertices, order G. Right, that's the average degree. Right, and the average degree, well, there's another invariant which I'll introduce independently, and that is simply the proportion of edges per vertex. So the number of edges of G divided by the number of vertices of G. And the two look sort of similar, right? So in the denominator you have mod G in both cases. You have the number of vertices. And in the numerator you have something different, but how different are they? This is the number of edges, and this is the sum of all degrees. Can anybody see how the two are related? Yeah?
We count the edges twice if we look at the degrees.
That's right. That's right. When we sum over all the degrees, every edge, which has two end vertices, gets counted twice. So that is twice that. So this is half the average degree. Okay, very good. Yeah, so we've got a few graph invariants already. And the average degree sort of measures globally what the min and max degree in the extreme cases or the individual degrees measure locally. Yes, there's a question. Mm-hmm. Yes, yes. That's why I put my finger there and made the finger hover over this for a long time when I said this is the number of vertices of G. That's my notation for the number of vertices of G is mod G. Okay? That is indeed the same as the cardinality of the set. Well, V is undefined, V of G. Right? By definition. And this, by definition, is the cardinality of the set of edges of G. Okay? Right. So we've got a few very, very basic invariants already. And in particular, we've got some local invariants and we've got a global invariance. These are not mathematically precise terms. This is just intuitive now. And let's set to work and see how some of these invariants are related. So what I mean by related, I mean things like, can we force one invariant to be large or small, assuming they're both numerical invariants, by doing something about the other invariant? So let's look at, say, the min degree and the average degree. Okay. So if this is large, then that's large. Right? The average is certainly no less than the minimum. How about the converse? If the average degree is large, is the minimum degree large? Well, not if large means the same thing. Right? So, for example, we could have a Kn. That's a complete graph on n vertices. Every two of these n vertices are adjacent. And we could have one lonely little vertex here, also in the same graph. And that little vertex has degree 0. So the average degree here is still pretty large. I mean, if you make n big as you like, it dominates this poor fellow there. So the average degree is large, but the min degree stays at 0. Okay, so that is certainly not true in the simplistic sense, but might it be true that okay, let me write it informally. If D is large, the average degree is large, is it then true that the min degree is large in some subgraph? Some, very important mathematical word. Some means there exists, okay? When I write delta is large in some subgraph, then that's shorthand for there exists a subgraph whose delta is large. Okay, now it becomes interesting. So in this example, yes, this has large average degree, and there exists a subgraph whose min degree is large. Now, these two larges don't have to be the same numerically. If they're not, what could we possibly mean formally? Well, we could ask, is there a function from the positive integers to the positive integers? Is there a function f such that I can force any min degree in a suitable subgraph as high as I like by assuming that the average degree of the original graph is large enough? So once more, informally, large average degree of G implies large min degree in some subgraph. Slightly more formally, the same thing says for every desired min degree of the subgraph, there exists an average degree of the entire graph that if I take any graph with that average degree, I'll find a subgraph of that min degree at least. Okay, so that's the slightly less informal way, and here's the really formal way. There exists a function, f, such that for every k and every graph G, k is the target min degree. The following is true. If the average degree of G is at least f of k, then there exists a subgraph H whose min degree is at least the desired k. Right? Are you getting that? Bit of a mouthful, right? This line, but that's a very, very typical line. That's the formalization of make this invariant large to force that to be large in some subgraph. Is there such a function? Not so clear. Here's a possible counterexample. Start with a kn. So that's a kn for n equals 4. And it has all vertices are large if n is large. Sorry, all vertices have large degree. So the min degree of that is large. And now I'm hoping to construct a counterexample to this. So now I modify this by inserting another vertex on every edge. Now suddenly the min degree is only 2. And this graph does not have a subgraph of large min degree. Right? It doesn't have a subgraph whose min degree is bigger than 2. But it's not a counterexample just yet, because it doesn't have large average degree, even if n is large, or does it? Okay, question. When n goes to infinity, how does the average degree of this behave? Degree of, let me call this kn with a dot, right? Every edge gets another vertex on it. When n gets large, how does the average degree of this behave? Does that go to infinity too? If it does, then we really have a counterexample. Why? Because we'd be unable to define f of 3. Right, once more. If the average degree of these animals for n large goes to infinity 2, then there is no such function because we'd be unable to find a value for k equals 3. K equals 3, what would f of k have to ensure? It would have to ensure that whenever a graph has average degree at least f of k, then it has a subgraph of min degree at least k. So for k equals 3, these graphs for n equal large would have to have a subgraph of min degree at least 3, but they don't. That's a contradiction only if we can't find such an f of k, which is the case if the average degree here goes to infinity, right? Because if it did, then no matter how we settle for f of 3, there would be a bigger n where the average degree is indeed bigger than f of 3, whichever one we settled for. And yet it would be one of those graphs, so there would not be a subgraph of min degree at least 3. So are these counterexamples? Is it true that this goes to infinity or not? What do you think? Not so easy to see, is it? Think of it, rather than in terms of average degree, think of it in terms of epsilon. Epsilon is the same as average degree, except for a factor of 2. So what does epsilon do for these graphs when n gets large? What's epsilon? Epsilon is the number of edges divided by the number of vertices, right? What does epsilon do for these graphs when n gets large? Well, the number of edges divided by only the white vertices is only 2. And divided by all vertices is even smaller. So all these things have epsilon less than 2. So they have d, average degree, less than 4. Okay? They're not counterexamples. But, I mean, you can see it's a puzzling question. It's not obvious. These are totally trivial graph theory. second lecture. No substance. But it's already sort of tantalizingly non-obvious. And that's fun about graph theory. Okay, then let's try and prove it. Okay, so once more the question is, intuitively, when we have vertices, when we have a large average degree, it can only be large if there are lots of vertices of high degree or a few of extremely high degree. And the question is, are they necessarily lumped together so that we can identify them as forming a subgraph of high min degree? Or can it happen that all the vertices of large degree are isolated as here? They don't conspire to form a subgraph between them that has large min degree, and still the degrees are large enough and there are enough of them to make the average degree large. So can this happen or not? Okay, we're trying to prove it can't happen. We're trying to prove that we can always find a subgraph of large min degree when the average degree is large enough. So how would we prove it? Yes?
Maybe with the pigeonhole principle, so that at some point we don't have any vertices left.
Where do your pigeons live? So the suggestion was use the pigeonhole principles.
I thought that if we have many more edges than vertices, so if the ratio is big enough.
Okay. Well, let me give a bad translation of your possibly good suggestion. The bad translation is, well, it's obvious. If we want to identify the subgraph of the vertices of large degree to form large min degree, then just delete all the others. Right? I mean, let's delete the vertices whose degree is below average. And then those of high degree are left. Are we done?
Then it's quite possible that we delete the vertices which make the one vertex.
Correct.
Vertices
Correct.
have a high degree.
Correct. So, of course not. Right? So if we delete all the vertices whose degree is below average, then the vertices remain whose degree is above average, which sounds like a good start, but the degree might have been large, i.e. above average, because they have neighbors amongst the vertices of low degree, which we've just deleted. And this is an example, right? So if we delete the vertices of below average degree, those are all the white vertices. Then we're left with the yellow vertices and they have degree 0 afterwards. So deleting all the vertices of less than average degree in G is not an option. Okay, second attempt. The correct proof goes as follows. We ask, or the idea is not to delete any vertex that has below average degree in the current subgraph, but to delete any vertex whose deletion does not reduce the asset that we have. And that's a very formal idea, proof idea, that is used a lot in graph theory. So let's just think, what do we have, what are our assets, what are the assumptions from which we want to deduce something? And then if we modify the graph, preserving these assumptions, the premise, the assets that we have, then we can't lose. Doing whatever we want, preserving what we're assuming, cannot lead us into a dead end, because the graph that we started with might have been one of those. right? If we have a statement saying all graphs that satisfy this or that have the following property, then if we modify this graph into something else that still has this or that, then attempting to prove that this has the property cannot be asking too much, because that might have been the graph in the first place. So what are the assets? Well, the asset is that the average degree is large. So let's modify the last step, the last attempt, and say we delete vertices one by one as long as what we're assuming is preserved, as long as the average degree doesn't go down. So that's a precise attempt, precise algorithm. Find a vertex, if you can, whose deletion doesn't lower the average degree. Yeah, then the average degree remains the same or goes up, and we can't delete all the vertices because when we have only one vertex left, the average degree is 0. So we have to end up somewhere. And in this somewhere, we certainly cannot find a vertex whose deletion would not bring the average degree down. And then we have to prove still that what we do end up with has large min degree. So let's see. Maybe the property of being able to delete that vertex without lowering the average degree tells us something about its degree. So that when we can't delete any vertices, every vertex has large degree, so the min degree is large. That's the aim. So what can we say about the degree of a vertex that we can or cannot delete in such a way that the average degree doesn't go down, yeah?
Doesn't that vertex have to have the average degree as its degree?
No, that was our first attempt. So that if we delete a vertex whose degree is below average, that unfortunately did not work. So let's think.
Not below average, just
Well, that's even worse.
okay.
Right, so suppose we're deleting this vertex. This is the rest. When will the deletion of this vertex not reduce the average degree? Well, if we're deleting at most as many edges as vertices, if the ratio between edges and vertices doesn't go down. Right, and now I'm talking about in terms of epsilon, well, that's qualitatively the same as average degree. So if this vertex V has degree at most epsilon of H, let's call this graph H, it'll be G at the start, but then it'll be a subgraph as we go along. If this vertex has if the degree of this vertex is at most the number of edges per vertex, then this is not going to go down because we're only losing these vertices, this many edges, and one vertex. If we delete one vertex and 7 edges, and the number of edges per vertex was at least 7, maybe bigger, then after deleting one vertex and 7 edges, we still have at least 7 edges per vertex. Right? We're not talking about these degrees here, just the number of edges per vertex. Yeah, that's clever. So we can do that. So we keep deleting vertices as long as their degrees in the current graph, H, is at most epsilon of H. And this will lead to a graph H, whose min degree is, well, we can't delete any more vertices, so this is bigger than epsilon of h. And epsilon of h, we made quite sure, was never less than the epsilon of the previous h, and ultimately than epsilon of g. So that's our theorem. Okay, so in the book, that's proposition 122. Questions? Nope. Okay, right. So I won't be able to do every little proposition in as detailed a way as I did this particular one, but I think this shows nicely how one gets to a rigorous statement with a rigorous proof from some vague idea. Vague idea meaning large average degree implies large min degree somewhere local. And we made this precise. Then we found the proof, and out of the proof came the theorem. We found the proof before the theorem. Right? Okay, yeah.
Should the degree of the vertex we delete not be smaller than the epsilon of g?
It will be. It is.
You wrote down it's smaller
Yeah,
than
it's.
epsilon of h. So
Yeah, but that is always. This is always smaller than epsilon of g. Because that's part of the proof. Right? At every stage, when we delete a vertex, we're making sure that the epsilon doesn't go down. We have a certain h, then we have a new h, and the new h has an epsilon that is at least as big as the previous h, whose epsilon is at least as big as the h before that, whose epsilon is at least as big as g. Yeah, other questions? Nope. Okay. Right. Okay, we're doing quite well. Then let's talk about paths and cycles. Okay, so what's a path? A path is a graph that looks like this. So more precisely, a graph is called a path if we can enumerate the vertices in such a way that the edges are precisely those between two adjacent vertices in this enumeration. So last time I defined a walk, and a walk is a sequence of vertices and edges such that something. A path is not a sequence such that something. A path is a certain graph, right? That's just sort of, yeah, we're in a different setup here. Paths are graphs. What's a cycle? Well, the cycle is a graph that looks like this, and the formal definition is take a path and make the first and the last vertex adjacent. If the path had length at least 2, the length of the path is the number of edges. Right? When we have a path of length 1, then these two vertices are already adjacent. We can't add an edge. So there are no cycles of length 2. That's the formal definition of a cycle. You can think of other definitions like, I don't know, you work in integers mod something and use the same definition as I did for paths. Okay, so an important aspect is that these vertices in the path have to be different, the vertices in the enumeration. So that's not a path, right? We have a walk from here to there in this graph, but this graph as such is not a path. A path cannot contain any cycles, and more generally, the graphs without cycles, the acyclic graphs, so those graphs that do not have subgraphs that are cycles. And now comes a terrible definition. I'm embarrassed even to announce it before I've said it. You can read it in lots of places. I get mad at all my students that make definitions like that, but I'm committing the same crime now because we can't use the real one yet. So acyclic graphs are called forests. What's a typical acyclic graph? Well, something like this. There's no cycle here. It isn't a path, but still there's no cycle. Yeah, that you would more likely describe as a tree. And indeed, a forest is more properly defined as a disjoint union of trees, except I haven't told you what trees are. Intuitively, trees are connected acyclic graphs, and you don't know what connected is yet. So let me make amends. G is connected if any two vertices are linked by a path. So for all u, v, when I write element of G, it could mean is an edge of G, it could mean is a vertex of G. I leave that to your generous interpretation. If there's really a possibility of getting this wrong, I'll write V of G. All right? So for every two vertices of G, there exists a UV path in G. Now, in means subgraph, and a UV path is a path whose first and last vertex, or last and first vertex, they're not distinguished, whose unique two vertices of degree 1 are U and V. I've just used the general amnesty. Have you noticed? I told you last time that graphs of 1 or 0 vertices have an amnesty. And I said every path, I said the unique two vertices of degree 1 in a path. Well, this is also a path. It doesn't have a vertex of degree 1, but it doesn't matter. It falls under the amnesty. Right? All other paths do have a vertex, indeed two vertices of degree 1, and any other vertices that don't have to be any other vertices. So that's a path 2, but any other vertices have degree 2. Okay, now you know what connected is. A tree is, and now to be really, really nasty, I could write a tree is a connected forest. I won't do that. So a tree is a connected acyclic graph, and a forest is a disjoint union of trees, at least one. It doesn't have to be more than one. So every tree is a forest. Okay, so much for more terminology questions. No. Okay. Now we get our next invariant. G of G is the girth of G. The girth is, well, how fat you are. So this is my girth, right? It's the shortest length, the least length of a cycle. What's the length of a cycle? Same as for paths, number of edges. Right, take a shortest cycle, any shortest cycle, it has a particular length, and that length is the girth of the graph. The shortest possible length of a cycle in the given graph. If the graph doesn't have cycles, if it's a forest, then the girth is, I don't know, infinity. Right? Okay, so that's the, yeah, sorry, yeah.
If we have one, let's say triangle and one cube.
Yes, you mean a 4 cycle? You don't mean cubed, you probably mean this.
Yes.
Right?
And if they're connected in one part, then is the side is the girth the number 3 or
Yeah, good question. Is it 3 or 4?
no 3 or 4 or 8? Like
Or 7, yeah. Or, yeah?
it's 3 because
It's 3. Right? It's the smallest length of
any cycle.
any cycle in that graph. And here's a cycle of length only 3. There is no shorter cycle in that graph. Indeed, there is no shorter cycle in the world than 3. So the girth of this graph is 3. Yeah. Mm-hmm. So we have a new invariant. Isomorphic graphs obviously have the same girth. So it's a new invariant, and we can try and relate it to the other invariants. And so what I want to try is to relate it to the min degree, as before. Oops. So let's see. Are those two invariants related? If the min degree is small, can we say anything about the girth? No. Correct. No. G could be large because you might be one long cycle, and G could also be small. You might be a triangle and then nothing else or whatever. So, what if G delta is large? Yeah?
I think you still can't really imply anything for G because, for example, if we imagine a lot of stars or like one vertex in the middle and then a whole lot of
Yes. Yeah. Oh, no. What's the min degree here? What's the min degree here? 1. So I want a graph of large min degree. So these vertices also have to have large degree, and these vertices have to have large degree. And the question is, does this force, let's say, a short cycle? Well, I want these many neighbors. All these have to have many neighbors, right? But these neighbors must not be the same, otherwise you have a short cycle. So is it possible that they're not the same, and you keep going, and you keep going, I don't know, for 2,025 layers, grow, always large degree. Every vertex has many new neighbors, until you have many million neighbors, vertices. at some point, you want to join them up again in such a way as to not create a short cycle. So there's the theorem, which is an intriguing theorem due to Paul Erdős. For every delta and every g integers, there exists a graph G with min degree delta of G bigger than the given delta and girth of G bigger than the given G. Right. Okay, so that will come at the end of the lecture course. All right, let me carry on now. How about d large forcing a large cycle? So we need a new invariant for that. That's the circumference of G. That's the longest length of a cycle. So when the min degree is large, do we need to have a long cycle? And that is easy. Right, so let's assume the min degree is at least 100. Then I can find you a cycle of length at least 101. And why? Well, that proof, very simple. That's proposition 131. Let's just start with the longest path. If the min degree is large, this longest path has to be long too, because this vertex is large degree, and if it's the longest path, then all its neighbors have to be already on that path. Otherwise, we could make it longer, right? So all these neighbors of this last vertex are on the path. So that's one, maybe that's another, and it has all its neighbors. So that's at least delta of G, many edges going out of this vertex. They all lie on this path. So jump to the earliest vertex and go back. And this cycle here has length at least delta of G plus 1. So even if we didn't omit any here, we'd still have delta neighbors and then plus 1 edge. So we get a cycle of length at least delta plus 1. Okay, so that's min degree versus girth and versus circumference. Next invariant is the diameter. The diameter of G is the greatest distance, the distance between two vertices is denoted by d of those two vertices. Any two vertices u, v in G. And what's the distance between two vertices? It's the length of the shortest path between U and V. So it's the maximum over the minimum of the path lengths between U and V, taken over all pairs of U and V. All right, so the picture is that if your graph is sort of has that shape, and these vertices are far apart, and the shortest path from here to there is still pretty long, then that will be the diameter. It's not this. Right? There may be some vertices here that are closer. The diameter is the maximum distance between any two vertices, so the maximum length of the shortest path between any two vertices. Okay, so how does the diameter, how is that related to the girth? Okay, so if the girth is small, does the diameter have to be large or small?
We saw in the example of we can construct a graph that has a very small
Cycle?
minimal cycle and then do whatever we want.
That's right. So we can have large diameter with a short cycle. So here's my short cycle, and a path, even if it's connected, these two vertices have very large distance, so the diameter can be large if there's a short cycle, and of course, if the short cycle is everything, then the diameter can also be small. So if G is small, then we can't say anything about the diameter. What if G is large? Can the diameter be large? Yes, of course it can be large. So you can have one big cycle, and the diameter and the girth are both large, yeah?
So could we at least the girth minus 1?
Yeah, okay, we're getting there. So that's, I've seen you. So the question is, if G is large, does it imply that the diameter must be large? Right? Or could it be that the diameter is small, that every two vertices have a short distance, and yet the girth is large? Yes?
I don't think that's possible, because if we look at two opposing vertices in the circle, and if there would be a shorter path between those two, the girth would be smaller as well.
Yeah, that's right. So that's indeed the idea of the proof. So let's make that precise. Let's assume that G is large. Let's take a short cycle of which we know it's long. So here's our short cycle. Let's take some opposite vertices, or as nearly opposite as possible. And the idea now was that these have to have large distance. So the diameter, which is the greatest distance between any two vertices, must be at least the distance between these two vertices. Why do they have to have long distance? Well, if there was a short path between them that is shorter than half the length of the cycle, then we could combine it with the bigger half of those two. I mean, they differ by at most one, but, right? We can combine it with one of these to form a shorter cycle than this whole thing. Right? If this length was strictly less than that length, then this together with that would make a cycle shorter than this together with that. Is that a proof? Huh? Yeah, morally, yes. Factually, not. Okay, how does the proof go? So we want to prove that the diameter is so this is 1, 3, 2. So the 132 says that the girth is at most twice the diameter plus 1. So suppose we have girth at least twice the diameter plus 2. Then we take opposite vertices, and then we know that there's a path between them of length at most diameter, and diameter is length less than this half, so we could complete the argument. That is the proof as it stands, made quantitative, except it isn't a proof because this distance means there exists a path, but not a path that forms a cycle with one of these halves. There might be another short path. Let me draw you a short path. Right? Clearly a short path. What if it looks like that? Okay. It starts on the cycle, it ends on the cycle, and it sort of maybe goes along the cycle for a little bit, and then it leaves the cycle, and then it can't go along the cycle all the way, because then it would be too long. Right? Along the cycle, this length is diameter plus 1 by definition, at least. Right? So this path is shorter, so it has to leave the cycle. It has to be different from half the cycle. But then we can take a subpath, call it P, of this path, from the first time it leaves the cycle to the first time it re-enters the cycle, which is at least there at the latest. And then we just talk about this P plus the shorter segment of the cycle between its end vertices. And both these segments, this segment's on the cycle and that segment on the cycle, one of them is no bigger than the other, right? So the shorter one of them is no bigger than the shorter one of these two. And together with his path, which is shorter than that, it adds up to fewer edges, and this now really is a cycle, right? This path union this is not a cycle, but this path union that, or indeed union that, are cycles, and one of those is shorter than the original cycle. End of proof. Here's a proposition. The proposition says it's 1 for 1. It says that if we have a connected graph, So let me give you a picture first. Here's a connected graph. And the proposition says we can enumerate the vertices in such a way that the initial segments always induce connected subgraphs. So we can enumerate the vertices, start with this one, say, and not take that as the next one, because we want the first two vertices to induce a connected subgraph. So we'd have to use one of those two. So let's take this one, and that's a connected subgraph, what they induce. So next one, not this, not that, not that, not that. Yes, that is possible. I could take this, or I could take that. So let's take this, and these three induce a connected subgraph. Then next, I could take this, for example. Oh dear, it's not connected here, but it's connected there. That's fine. Then I could use this, and so on. So I can find an enumeration of the vertices whose initial segments induce connected subgraphs of G. Can I always do that? Yeah, of course I can. How do we formalize that? Not quite so clear, but it's a trivial but interesting example of a recursive definition. So define the enumeration V0, V1, Vn recursively as follows. What does it even mean to define it recursively? Recursive is the same as induction, except for defining things rather than proving things. So it applies to integers, to natural numbers, and we can define for every natural number something, assuming that we have already defined it for smaller natural numbers. And that's what we do here. The rule to pick the vertices is to pick the next vertex. We start with any vertex, V0. And when we get to picking Vi, we may assume that the vertices which, or we do assume that the vertices that we've picked so far up to Vi minus 1 form something connected. Maybe they do, maybe they don't. If they don't, we stop and throw up our hands in despair and say, we're stuck. We can't go on defining. If they happen to induce something connected, we say, oh, great. Then define Vi so as to be adjacent to something in here. Not necessarily to Vi minus 1. But just to something in there. Right? Now, that's a rule for how to define vertices one by one. Each vertex Vi gets defined with reference to some property that the previously defined vertices have, and they may or may not have it. And if they have it, we know how Vi is defined, or could be defined. So this recursion involves a choice that's allowed. Right? The definition says, take as Vi any vertex that you haven't taken so far, which sends an edge to one of the vertices that we have so far. And whether or not such a vertex can be found is something we don't know at this time of definition. Okay? Cut, new chapter. Let's define that this rule really works and gives us an enumeration as we wanted it. And now we prove it by induction. So we prove property by induction And the induction is along, I call it along the recursive definition. And that works as follows. We first prove it for the graph that only consists of V0. What is the statement that we're proving? The statement that we're proving is the vertices up to this one, V0 up to Vi, induce a connected subgraph in G. That is true when I equals 0, because R, not true, oh dear. Because I haven't told you, oh no, I have told you. No, that's fine. The one vertex graph is connected, the empty graph isn't connected. Okay, so the one vertex graph is connected. Here, I couldn't count on the amnesty because I'm starting the induction, so I got a little into jitters here, but everything's fine. So V0 by itself is a connected subgraph. Okay, then, in the induction step, I have to look at V0 up to Vi and prove that they induce something connected. Since I'm using induction, I may assume that V0 up to Vi minus 1 induce something connected. Now we're assuming that, and remember, how was Vi defined? Well, Vi was defined by saying, if V0 up to Vi minus 1 happens to be connected, then I'll give you a Vi. And we say, oh goodness, yes, great, we have a Vi. Or we could possibly have a Vi. Now the definition then said, find a Vi that sends an edge to what we have so far. Does that exist? Yes, it does, because by definition, the graph is connected, so if there's any vertex left, there is a path to V0 in G. And this path has a first vertex amongst V0 up to Vi minus 1. And the last vertex before that we take as Vi, not the one we found so far. Okay, so I've now shown you that if the assumption is true that V0 up to Vi minus 1 does define something connected, span a connected subgraph, then we did in fact find Vi in the recursive definition. Why? Well, it said if this is disconnected, then stop, do nothing. We know that isn't the case, so this is connected, so we can do something. And then it said find a vertex that sends an edge to it. We've now shown that such a vertex exists, and therefore we know that the recursion chose one of those. Right? We don't have to now say which one, where we're allowing choices here. Okay, but now we can continue with our inductive proof that V0 up to Vi span something connected in G. And that is true because this was connected. What does it mean? It means that for every two vertices, you can find a path in there. Now, adding this, all we know about this vertex Vi is that it sends a vertex to something in here. So is this still connected? Yes, of course it is. Between any two vertices that we had already, there was a path in there. And this sends a path to anything in there because we just go to this vertex and then we use the old path. Yeah, so that completes the induction step, which is very confusing, isn't it? I mean, it's a very, very simple idea, and to make it precise, formally precise, we have a recursive definition, and based on the recursive definition, we do an induction, but that is something you sort of have to upload into your subconscious. That's the sort of proof you need to get used to, and I spelt it out in such detail here, and we don't normally do that, but somebody will notice if you think you got it right and you didn't. Any more? No, one more. One more definition. Questions about this proof? You're okay now? No. You just had answers, no questions. Yeah, very good. Yeah. Okay. One more definition, and that is that of a component. A component of a graph G is a maximal connected subgraph. When I say maximal, and I don't say anything else, I mean maximal with respect to the partial ordering subgraph. Maximal always refers to some partial ordering. I used maximum earlier when I spoke of the maximum degree. That refers to a number which is greatest, which of course also the numbers also have a partial ordering on them, right? But something is maximal if it is a maximal element of possibly many in some partially ordered set. So a partially ordered set can have many maximal elements. So in the usual drawing for partially ordered sets, so higher on the board means bigger. This is bigger than that. By transitivity, this is also bigger than that. And this is also bigger than that. This is bigger than this and this and this, and also than that, but this is not bigger than that. Okay, so that's the explanation of this diagram. And this has 1, 2, 3 maximal elements. And it has 2 minimal elements. Okay, so a component is any subgraph that is connected and is maximal in the partially ordered set of all connected subgraphs. What do these things look like? Well, here, this graph has 2 components. This is connected. Is it a component? Yes, because any subgraph that properly contains this as a subgraph is disconnected. This is maximal in the partially ordered set of connected subgraphs because there does not exist a connected subgraph of G that contains this properly. When I add anything here from here, the union with this would no longer be connected. Right? So if I excluded this vertex here and asked, is this a component? The answer would be no. It's connected, it's a connected subgraph, but it's not maximal because here's a bigger one. Right? Bigger under the subgraph relation. The earlier subgraph of G is a proper subgraph of this subgraph of G. All right? So beware when I use maximal and minimal. They always refer to partial orderings. And if I don't say anything, the partial ordering is going to be that of subgraph. It might be something else. It might be induced subgraph. And it might be yet something different, which we'll get to later. But that's as much as I want to say. You need components, I think, for the exercise sheet. You need trees for the exercise sheet. And that, I think, is all you need so far.